Record it. Um, so what Matt's asking about is the ability of the CMB's temperature variation. The largest one that there is caused by the Earth's all of the vector velocities of a spacecraft, of a telescope, including the Earth's motion, the satellite's motion, the sun's motion, the solar system's motion, the galaxy's mo all those vectorial sums, which are completely unrelated to each other, in that today is June 13th, and the position, we're getting close to summer solstice. The all those things are completely irrelevant to say the Earth's velocity with respect to the Virgo supercluster. So, but the fact is, you can use each one of those has a Doppler shift component that contributes to the net Doppler shift that we see, which is what produces what's called the CMB dipole. Now, what Matthew's saying is that some experimental physicist that he heard at some conference was suggesting that that has only been measured from space, and it had only been measured by one satellite, which was called COBE, Cosmic Background Explorer, and that had results in 1992. And those are actually the results that inspired me to become an experimental cosmologist. And the follow-up to that instrument was called WMAP. WMAP also measures the dipole. And WMAP, the W in WMAP is my PhD's advisor's PhD advisor, David Wilkinson. So I have a good connection to all these guys. So what the WMAP instrument and what Planck and COBE and all the other instruments measure is the sum of all vector contributions to the Earth's or the whatever detectors making the observation, all those added together produced what we observe as a dipole, a Doppler shift. It's hotter in one direction, one hemisphere, it's colder in the other hemisphere. And that is an astrophysical source of microwaves that we use to calibrate the response of our temperature sensors that are, in our case, Simon's Observatory, called the bolometer. So there are many instruments that can measure it. And in fact, we need it for calibration, in particular, calibrate the temperature response of all the detectors. So this is why I think it's maybe being misapplied, or I'm not sure who was saying and what their claim was. Matt, you can tell us what specifically you think it was, but it's one of the most precisely measured and calibrated sources that there is.
Okay, so you at the Simons Observatory or on BICEP, what those experiments, you guys did measure the CMB dipole.
The polarization of the dipole is zero. So we're polarization instruments. So we don't measure the dipole because it doesn't tell us anything about calibration. It does, on the other hand, tell us about the absolute temperature and distribution of the microwaves, which we do use for correlations with the polarization. Because you learn a lot from asking, well, how correlated is the polarization signal in a given direction at a given spot in the sky with the temperature of the rest of the sky in different locations, perhaps far away from it. And our ultimate goal at the Simons Observatory is looking for inflation, looking for these primordial B modes, which are not, there's no dipole component. There's nothing relevant about the dipole that gives us any information. That said, if we wanted to measure it, we could because we have the sensitivity to do so, and we're on a moving planet with different vector velocity. So another way to think about it is if you have a telescope on Earth that's measuring it, in the daytime when the sun, is moving in a direction, let's say the sun right now is moving towards the direction of the velocity gradient caused by the Virgo supercluster, which is pulling on the Milky Way and Andromeda and the local group of galaxies. So let's say in June during the daytime, the Earth's velocity is parallel to that velocity vector, or has some component parallel to it. Well, then 12 hours later, it'll be anti-parallel or opposite to it. So it'll subtract a little bit of the velocity. We can measure all those different vector contributions. So we have a very accurate 3D model of the Earth and the Planck satellite and all these other satellites and the Simons Observatory, and we can see the modulations and they come out perfectly as expected. So that means that they can be used for calibration of the signal, and that's how we use it. So yeah,
That's
so
awesome.
I'm not sure what the claim was, or you have to send me an email with the name of the person that was making the claim. But can you say more about this conference? I know nothing about it. Sounds interesting.
Right now, they had their first conference down in Austin, Texas last year to coincide with the eclipse. happened
Uh-huh.
to go out to that. I mean, it was an interesting day. It was cloudy in Austin, and we had a telescope with a filter there. We couldn't, by peak eclipse, you couldn't see through that, but there was just enough cover. You could actually see it. And again, maybe I fried my retinas, but you could see it through the clouds and actually take a decent picture on your iPhone and it looked like the general picture of a black hole. And that
Yeah.
was really cool. So,
That's yeah,
uh,
that's very beautiful image that you get to see. Yeah, I was gonna make it out there. I was supposed to bring Joe Rogan to go see it at a friend's house, and then he was too lazy in the end. He was like, I don't, my wife and daughters just want to stay home, so we're gonna stay home. I'm like, all right, you'll just wait for the next one in 2046.
well, yeah, yeah. I mean, it is what it is. But we're in Sombra, Portugal. It's a gorgeous day. They have live music and everything, and we've got a bunch of heretics from anywhere between Professor Unziker, your arch nemesis Eric Lerner,
Is he there?
is here. Yeah, yeah,
Wow.
he is here, and Anastasia offered to have to moderate a friendly discussion between you. I said, listen, you can do whatever you want, but I would prefer personally to just see a friendly discussion with folks that maybe you both know and just be like, list some things in a friendly fashion and just go through rather than the video wars and stuff. Then again, that is good for clicks. So I'm like, I'm just throwing that out there. But no, it's interesting. And there are, even though it is a conference mostly of heretics, people are pushing back. They have some more mainstream folks that are willing to say, no, this that maybe there is a bit of a helium problem. Maybe this is a thing,
Or a
but push
lithium
back
problem. A
and
lithium
oh, the
problem. Yeah.
lithium problem.
Yeah, yeah,
Okay,
yeah.
pardon me.
Right. The
But they're
helium is
going
a
through
problem for
and
them. Yeah. The helium
yeah.
and every other element's a problem for them, but there's one element that's a so-called problem. But we call it the problem. So, it's not like we don't know about it. But yeah, Lerner's a character. I've never met him, but yeah, it would be interesting to I don't know, debate maybe. I don't I'm speaking at this How the Light Gets In festival, which I think he spoke out before. But yeah, I didn't know anything about this conference. I mean, they've interviewed me many times in person, Anastasia and Shiloh. But how many people would you say are there at the conference?
Well, it's probably maybe 50 or 60 or so.
That's pretty
That's a
big. Wow.
decent it's a decent conference and they originally wanted to rent a castle, but
Wow.
they realized like renting a castle in the summer for 50 people probably was very hard, so
Yeah,
they
that's
chose
ambitious. Yeah.
yeah, no, just very nice hotel whole here, basically around the Mediterranean area.
Oh,
We're
wow.
basically just on the Atlantic right before it curves down, but it's
Yeah,
very
I've never been
lovely.
there to Portugal or to yeah, Spain. So yeah,
I have
no.
a question for you on Lerner. Is he the guy that says that the surface brightness is flat all the way across? Is that who you're talking about, or
He's the one who wrote a book in the 90s called The Big Bang Never Happened. And he's, basically been going on about that for decades. Oh, hold on one second. I've got another caller coming in. Darren, Tim, can you hear me? Can you guys hear me on X? Got my X team there. Well, hopefully you can hear me. Darren. Sorry guys. Yeah, so Michael, you were asking about Eric Lerner. Yeah.
I think it is. Sorry to cut it because I think that I did hear him say something about surface brightness and luminosity, and that's what he was talking about earlier. So I do believe it. I think it's the same guy. I
Oh
could
yeah,
be
it's
wrong.
certainly the same guy. I mean, he definitely feels like he has that he has a claim. Hello, can you hear me on X? Hold on, sorry guys. Hello. Oh, great, great. So we got a bunch of people on now. We got a couple on Zoom, a couple on Twitter. Great. So just let me know if you want to ask any questions. Just, raise your hand or do whatever. Right now, just discussing my good old friend Eric Lerner. So yeah, so Lerner's gotten a few different claims. I mean, I think the one that is, most significant is that the Big Bang didn't happen, which is that all the evidence that we have for the hot Big Bang is either wrong or inconsistent with observations. And furthermore, he then claims that the reason that we all say this is because we're essentially, in the pocket of some, anti-fusion technology, or we have some goals that's not entirely scientific. So he does that by looking. I mean, there's three main features of the Big Bang Theory that we really hold up as pillars of the truth and veracity of the model, which is how any good model should be apprised, which is does it match evidence? And so for the Big Bang model, there are three major pillars: that there are galaxies in the universe distributed more or less evenly on large enough scales. They're all redshifting away from us beyond a distance scale. The origin of the light elements, the periodic table that cannot be produced in stars, the isotopes of helium, deuterium, and tritium, and helium-3, helium-4, lithium 7, beryllium 8, etc. Those which we know cannot be produced in substantial numbers in stars. They are produced, their abundance relative to hydrogen, protium, is a prediction of the Big Bang model. And then finally, the CMB, and anything that also acts like the CMB, like baryon acoustic oscillations, the source of the recent DESI controversy that I talked about with Eric Weinstein on the podcast a lot recently. Those are the three pillars. So for each one of those, Lerner claims there's some flaw that we're just not understanding, and that in his model, which he doesn't really have a model, his model is it's a steady state. The universe, there was no Big Bang, the universe is not expanding, and the universe is a finite, an infinite age, and that photons are decreasing in their redshift. Their wavelengths are increasing, frequency decreasing due to the fact that photons are losing energy. So this goes by the general term of tired light. You've heard of that, Michael?
Oh
And
yeah, I've heard of that.
yeah. And so he claims that that's the then now for the CMB, he claims that the CMB is also the result of high redshift, constant surface brightness sources that are also being diminished as photons travel. So they're more highly redshifted because the photons that he's talking about originate in the optical or infrared and then make their way to the millimeter wave. That's a factor of 1,000 in redshift that he has to account for, but he does that by absorption by dust. So all of these were original claims against the Big Bang in the 1930s and 40s, except for the CMB, which wasn't discovered until 1965, 50, 60 years ago exactly, this last month. So he has to come up with reasons for that. All of them are ridiculous. They've all been contradicted by evidence. There's not only abundant evidence for all those features of the Big Bang, in that there is abundant evidence for expansion on all scales. There's abundant evidence for light element abundances. And then there's abundant evidence for the CMB, baryon acoustic oscillation, Sunyaev-Zel'dovich effect, temperature anisotropy, polarization anisotropy. So not only are all those 10,000 different data points that are all independent of each other, supernova, I didn't even talk about supernova data, those also go in there. So there's tens of thousands of individual data points that each one of which, except for one data point, which is the abundance of lithium, which is only discrepant at barely more than 2 sigma discrepancy. We can talk about what that means if you want. But the overall consistency of the Big Bang model is hundreds of sigma. And in contrast, the steady state model is ruled out at tens of thousands of significant figures. So there's zero, really, truly zero evidence for the steady state model anymore. And only because he will be able to find people that believe in some alternative to the Big Bang will he want to justify it. Now, that's not to say the Big Bang doesn't have challenges and flaws, but those are not consistent with his model. And everything that we know is consistent, at least back to one thousandth of a nanosecond after the Big Bang. So whether or not the Big Bang actually happened is, perhaps always open for discussion. But we'll have to see where the data come in that refine our model of the Big Bang. In other words, more observations of lithium, et cetera. But there's zero evidence, and there's no even proposed way to get evidence for the steady state model. So it's really a dead extremely dead and bad science effectively to do this. It's like it would be like denying DNA. Imagine if like every organism on Earth has had its DNA sequence, and then you have this theory of Lamarckian evolution that doesn't involve DNA and heredity. And it's ruled out, thousands of by every species, every chromosome, every phenotype of each genome. And so there's literally tens of thousands of standard deviations against you. So that'd be kind of like what he's doing. But because people don't understand general relativity and there are admittedly, holes in some of our initial understandings of the initial conditions of the universe, that he believes that. But this is something he's been thinking about, talking about for literally 30 years now. When the Hubble Deep Field first came out, and got a lot of attention 3 years ago when the Webb telescope deep field came out.
What if the brightness thing, he shows like that it's just flat. What do we actually think the brightness of galaxies are? Is it to the negative fourth power, or in z plus 1 to the minus 4 power, or what? That's what the Big Bang predicts, right?
That's right. Yeah. So
And
that's
what we measure is it 1 plus z to the minus 3?
well, what he claims is that it doesn't show this, but the data sources that he's using are sort of cherry picked. He picks essentially the data sources that don't demonstrate the dimming, but he does ignore. So there are data sets that don't show as strong evolution, in particular, the very most distant galaxies. For which you have this selection effect that you can only see the brightest galaxies.
Right,
And
for sure.
if you don't correct for that, and each galaxy suffers from the following two diminutions, and the reason you get z to the fourth is a combination of effects that the number density of galaxies in an expanding universe goes down as the scale factor, which is basically the size of the universe, the radius of the universe expands. If it doubles, the volume goes up by a factor of eight. Therefore, the density goes down by a factor of eight. Therefore, all the photon energy density goes down by a factor of eight. But also, the energy of each photon is dependent on its redshift. So you get another power of the scale factor redshift. So that's where you get z to the fourth power in an expanding universe. This is known to be true in every single source that we look at, except for the individual brightnesses of galaxies. The problem is, what is a galaxy? To define the actual diameter of a galaxy, for example, is not a straightforward exercise. In other words, to say, well, a Milky Way-like spiral galaxy, depends on, it's like a fractal. It depends on the size scale in which you use for your ruler. If you measure the coastline here in California using a micrometer, you get a different result than if you use a kilometer long LIGO sized measuring stick laser interferometer. You get very different results. So too with galaxies. Even for elliptical galaxies, if you ask the question, well, if you saw a planet and I tell you it's an Earth-sized planet, and you say, well, I don't measure the same size as the Earth, therefore it's not an Earth-like planet. It's kind of ridiculous because the Earth has an ill-defined, what is the diameter of the Earth? Is it exactly the average value of its radius? Is it the atmosphere as well, which decays exponentially and
Right.
therefore is not broadly defined, well defined? So you can cherry pick those things. Now, the question is not, as I tell my students, it's never what the value that you measure is compared to your theory. It's always how much you quantify how ignorant you are of what you've measured. And my main criticism, he never quantifies his values uncertainties. He never gives standard deviations of discrepancy. He only will show some value. So he'll plot these plots that show, oh, it's decaying or it's flat. But the individual galaxies have error bars on them. Yeah, so thanks, Matt's showing it. Can you put that
So
up?
this okay, so this
Yeah.
is something that was here. It might be inverted going through, but it's helium abundance. Hold on, let me read.
Yeah.
Helium abundance far too low in local stars for Big Bang predictions. I mean, I kind of look at this and I'm like, well, you could depending on your error bars, which totally matter, you could plot it differently.
Right.
So,
So the what you do when you have data that have error bars, which he never has produced a single data point, he's just using real scientist constructions and their data that's provided, which is fine. You can look at data, that we publish, and you can. I'm not saying you have to be a member of the team or some special cabal to look at the data. You can look at it, but it's dishonest to present the data as he did recently with the lithium abundances. He doesn't plot the uncertainty. So let's say I tell you that your car is moving 1,000 miles an hour, and therefore you're going to get thrown in jail. Well, if I don't tell you that my uncertainty on the radar gun or my watch is equivalent to 2,000 miles per hour, then it's totally useless. Now, if I say you're going 1,000 miles an hour, and I know that to within a proton, Planck length per nanosecond, that's pretty good. What he fails to account for is both there are two types of uncertainties. There's statistical uncertainties based on the lack of samples of a measurement. In other words, if you measure the width of the table you're sitting at thousands of times with a ruler, you'll get a closer and closer and better value the more times you measure it. It'll not improve linearly, it'll improve as the square root of the number of data samples you take. But on the other hand, if your ruler is a half inch too short and you don't know that, and so you think it's 12 inches long and it's really, or a meter stick or whatever, you're going to make a constant, what's called systematic error. The only way to get rid of a systematic error is to make a measurement of calibration of the measuring tool itself. So in those data, there are statistical uncertainties and there are systematic uncertainties. Furthermore, that's in the observations and the telescopes, for example. But then there's also theoretical uncertainties. If you ask, well, how fast is this galaxy moving? Well, that depends on the theoretical gravitational pull of the Andromeda galaxy on the Milky Way, for example, which even in pure Newtonian physics, which is all we really need, has Newton's capital G in it, which is actually quite poorly measured, or quite imprecisely measured, shall we say. So that's a theoretical uncertainty that you also have to account for. He accounts for none of it, neither in his own models, which don't feature these factors, and he does truly ignore the overwhelming, complete lack of evidence for anything like the tired light model. There's no evidence for the tired light model. You could test it very easily on Earth. We can test to 14 decimal places. The speed of light is constant over all Earth-sized distances, all the way out to the Voyager 1 satellite, which is more than 1.25 light days from the Earth. There's absolutely no deviations from it. So in other words, Voyager 1 sends out a signal, and it's precisely at 1400 megahertz or something like that to get to its transmitter back receiver on Earth. We have to measure that to within 0.1% uncertainty, because if we didn't, the signal is completely undetectable. It's even hard to detect normally, but if you don't know the frequency that you're on, you mistune the radio dial, you'll miss the signal completely. Now, if the tired light model were true, all of space is expanding. Therefore, the distance between us and one light day would be expanding. And there's no evidence for that at the 14 decimal places level, even though it manifests itself at much lower levels and easier to detect levels. So it's completely nonsensical. I don't know why he doesn't just say there's problems with the Big Bang model, but the fact that he proposes an alternative model is what's so problematic for him. That there's zero evidence. There's almost a near deluge of data against him that he just ignores. But if he were smart, he would, which I don't think he's dumb, but he's so obsessed with the death of the Big Bang model that he actually does himself no favors, because he could actually have a strong argument that we need more research, and my colleagues have done research to show that maybe lambda CDM is wrong. And we have to do it, but they don't come out and say, well, because lambda CDM is not perfect, therefore it's completely wrong. It's all or nothing. It's either completely right or completely wrong according to Lerner. And they don't propose another model that's as different as, say, DNA hypothesis is from the triple helix. Let's say Linus Pauling believed the DNA was a triple helix. There's a near infinite amount of data suggesting Linus Pauling is wrong, and that the DNA double helix is right. So Lerner's kind of in the triple helix camp, but also saying that the double helix is wrong. So it's really bizarre how he operates. And so, but he gets a lot of attention, gets invited to these conferences. So, he gets donations to his fusion reactor, which apparently, is some big concern. And they've raised tens of thousands of dollars from individuals. So that's pretty interesting.
I mean, my greatest criticism would probably be if you're going to state the Big Bang never happened, yes, that's a headline thing, but it's like you pointing out, Professor Keating, if there are some issues with the lambda CDM model, James Webb is coming back with some very interesting observations, and again, we need to go through it and do different confirmations and apply our theoretical models the best we can. My big thing is to state that it didn't happen. I wasn't there. I don't know, but I'm curious
You don't have
in
to
the
be there. Yeah.
evidence there.
Yeah.
And again, it's
I wasn't there either.
probably one of, yeah, my other criticism is if Eric Lerner wants to put out Eric
Say that
Lerner
again.
stuff,
Yeah,
that's
memes is here.
totally,
Yeah.
oh
Sorry.
yeah,
Yeah, it's Matt Fox, Memes of Destruction, and then Michael Sarnowski are on here.
yeah,
Can you hear
it's
us
just,
okay, Darren? Okay, I can hear. Okay, cool. So go on, Matt. Sorry, Darren was just checking in.
no worries, no worries. Good to have you here, Dan.
Yeah,
My thing is, if Eric Lerner wants to put on the Eric Lerner channel his opinion, that's fine. My thing
right.
is, if you're gonna put that out on your company's channel, I feel like those should be different things
Yeah,
personally.
I don't get it. That
Because
the
I'm interested in the fusion stuff, but it's
Yeah, the fusion stuff is interesting. I mean, be interesting to take a look at his fusion because, if it's as kind of off as the Big Bang challenges that he presents, that could be problematic. But for investors, so I mean, he has a lot of basically things at risk because he has investors and he has donors. And if he's, kind of being sloppy or not being precise with his donors, I would want to know more about that and ask some questions about the stewardship of my money. But I'm not going to send a team of 60 Minutes reporters to his house. But it's just curious to me that there's so much anti-science sentiment that people are so distrustful, hostile to practicing scientists that they, are actually coming up with claims about things like this that cast doubt and where there really is no doubt. I mean, there are doubts about what happened at T equals zero. I just talked to Stephen Hawking's final and some say his best collaborator, Thomas Hertog, yesterday, who wrote a wonderful book about his life with Stephen Hawking and the final theory that they worked on. And we know for a fact that there's a lot wrong with what Stephen Hawking thought about the Big Bang and even black holes and various other subjects. But that doesn't mean you basically say that he was, lying or there's some ulterior motives and he's grifting and all the kind of complaints that I always hear from people like Lerner.
You
So, yeah, go ahead, Michael.
oh yeah, with the brightness thing,
Yeah.
the I think there's a guy named Lubin, where they come up with the brightness is like 1 plus z to the minus 3 power, for like closer galaxies, and the farther ones are more like 1 plus z to the minus 2. But you're talking about like there's like a filter where we can't even see most of them, so we can't really actually get a really good gauge on the farther galaxies. Um,
Right. Yeah. I mean, he's basically
so
saying, but he doesn't account for how these galaxies got there.
who
Yep.
who is who is
He,
he?
Learner.
Oh,
So he's basically saying that the z to the fourth should be z to the three, right?
no, I think he's saying z to the 1.
I think he's taking it very linear. To my knowledge, when we're saying z to the fourth, are we talking temperature to the fourth power and its relationship with redshift? Is that what we're
No,
talking
he's
about?
talking about these go back over 10 years, that again, what typically happens with him is that a new result will come out from a very distinguished team about some other fact, like like trying to measure just the surface density of galaxies in the early universe with the Webb telescope when those results came out. Uh, just as he did 30 years earlier with the Hubble Deep Field, he claimed there's too many spiral galaxies. Well, that wasn't the point of that image. first of all. And second of all, it's not inconsistent with, they're both perfectly consistent with each other. It's that Webb saw deeper back in time because it had an infrared sensor that Hubble lacked in its image. The ultra deep field doesn't have, I mean, Webb was designed to primarily do infrared astronomy, which means it could go sensitive to longer wavelengths than the optical wavelengths Hubble was sensitive to. So these ultraviolet galaxies that emit energy in the 100 nanometer wavelength region, those get redshifted to, almost 1 micron. So factor, hundreds or, tens to hundreds rather. And that makes it very plausible that you could see them in the Hubble and in the Webb telescope. So he claims that, again, he's claiming that it doesn't fall off as that 1 over redshift to the fourth power, even at these relatively high redshifts. But there's a complete lack of how the error bars are analyzed. In other words, he wants to show that these things are, if you were to plot it, I'm sketching, with my hand in the air, but if you want to plot it, it would go very sharply as a function of redshift. So if you measured something at z of 1, it would be 10,000 times brighter. The surface brightness of that
Right.
galaxy be 10,000 times bright. So now a dynamic range of 10,000 to 1 is not implausible, but it's very difficult to measure the flux to that level of precision at high redshift because these things are very dim. But he doesn't have an explanation why these things are so dim. He's just saying that they should be much brighter in his model, but he's not correcting for the fact that what this bias that I talked about is that you only see the ones that are brightest. You only see these intrinsically high surface brightness galaxies. So therefore, it's going to inflate the ones that you do see. That doesn't mean the ones that you don't see aren't there. So what astronomers do is correct. It's called Malmquist bias. And that means that you artificially are inflating how many high Z galaxies you see, which means that you could fit it, you could see that they're actually more consistent with a less sharp fall off in Z. Does that make sense? He wants to say that it's not Z to the 0 power, which is a flat trend or something like that, as I understand, or Z to the -1. So Z to the
I
minus
think
one,
it's
yeah.
flat or
Flat,
whatever.
yeah. So
But
flat, but so you can be tricked into thinking that it is flat if you neglect the fact that you're not likely to see a low surface brightness galaxy. But remember, he's trying to say that all the galaxies have the same property, but we know for a fact that the galaxies that are closer are even as dim as they say that they are because we can measure and correct for this Malmquist bias. There's another thing that he always neglects. He neglects this particularly in the lithium, but certainly with the surface brightness. He assumes that galaxies are eternal. Let's ignore the implausibility of that. Like, imagine that our sun is not evolving, that he has no explanation for why supernova occur, by the way, and why they occur at the same rate in every galaxy that we see, and why we see different amounts of supernova and different ages of stellar populations in different galaxies. So he has to ignore all that. But so basically, he's saying that stars are eternal, which is completely against all laws of not cosmology. So now he's contradicting just the laws of stellar evolution, which have been around for 100 years.
Is
So
is that something he said? Because I didn't hear any of that here. He and again, uh, not
I
if
don't
you're
think that he
just cherry
gives out,
picking the
his
data, but
greatest. I think he does his greatest hits. I don't think he goes into all the ways that he's been demonstrably falsified in the past. But
he
you
gave you guys deuterium.
say that again.
He gave you guys deuterium. He's like, oh yeah, no, Big Bang, deuterium, and that was it. And I'm like, that I don't think that's the case because it's like I've listened to plenty of your podcasts and other different professors, and I'm like, maybe even if you have some doubts about the standard lambda CDM model, it's just I'm like, but I think that stuff kind of lines up there, and it's like this. I don't know, like
Oh
why
no, it
why
definitely
do you?
does. Yeah, I mean,
Yeah.
there's no serious cause, and it's not for lack. I mean, remember, there's 3 people in my department that study string theory. I mean, it's not because we don't want to test alternative explanations. It's that when an explanation has been thoroughly ruled out, like let's say he doesn't believe in the laws of thermodynamics, and he's got some alternatives. Well, Stephen Wolfram, who's coming back on my show on Monday, Stephen Wolfram or Sabina Hassenfelder is coming on Tuesday. They have different ideas for the origin of the second law of thermodynamics. Stephen Wolfram characteristically thinks of it as much, in his, physics, in the Rulliad way of things. So he thinks he has an explanation. He doesn't say it's wrong, but sorry, let me see something. Someone's asking a question. Give me. Uh, let me just type to them. So he doesn't say it's wrong. He just says, here's my interpretation of it. Like we have interpretation for quantum mechanics. There's nothing wrong with that. If Lerner wants to say, but if he says the second law of thermodynamics is wrong and that entropy does not increase in a closed system, then it's just ludicrous. We wouldn't hire somebody like that. That person effectively is arguing for perpetual motion as reality. So there's no need to entertain such people because there's literally trillions of standard deviations of evidence against them. So when a person doesn't agree with the evidence, that's on them, but we're not going to let them teach people, and they're not going to get papers published, and they're not going to get patents and stuff like that, which is why I do have my suspicions about his nuclear fusion ideas, because it's so sloppy. It is kind of a tantamount to someone who believes in perpetual motion machines, which would be very dangerous with nuclear fusion. So I wonder, is the Atomic Energy Agency, is the Department of Energy, are they involved? Like, what if he's making some weapons or something? I mean, so I'd be curious about that. If someone would look into, the kind of claims that he makes in fusion, I wonder if they're as imprecise, cherry-picked, or falsifiable as the claims that he makes about cosmology. But again, getting back to, so deuterium is it's like saying, well, I'll give you the fact that the Earth, from space looks round. But I actually know that's flat, because we have these I don't even remember what the main claims about flat Earths are. Is just that gravity, you fall off the edge, or things look. I
It
mean, there's
makes
so much
stairs
evidence
very
against the
difficult.
flat Earth. What was that, Michael?
It makes stars very difficult, or stairs very difficult.
Oh yeah, yeah, right.
That wasn't
Uh,
me.
so Michael, what were you saying? I'm sorry, I interrupted.
Oh, that it wasn't me. I had just asked you a question um if there's anything, or I always thought maybe we get off of this subject,
Yeah,
but
yeah,
um,
we can get off
um,
that subject. I think we've talked about Lerner enough.
but I had a question about filaments versus voids. Do we see
Yeah.
a big difference in the velocity curves for equal looking or equal mass looking galaxies, I guess, voids versus filaments?
So specifically, what are you interested in? I interviewed David Wiltshire, who's got the timescape cosmological model. That's a very important contribution to his model. Are you familiar with that?
No, no.
Okay, so that interview will be out in a while. I'm blessed but cursed, because I've got, amazing interviews,
Right,
but they're not. I can only get out one a week, because I have a day job, right? But so velocities and first of all, let me explain what a filament is. So on local scales, the average density of matter in the universe, in the Earth, is trillions of times higher than the cosmic average. You have to ask, well, how big a box do you have to get out to before you can say the properties of that box, the density, the pressure, the number of filaments, the statistical mechanics of it are representative of the parent universe as a whole. And that turns out to be quite far. It turns out to be like hundreds of megaparsecs, so 300 million light years away. Because if you just sample near the Milky Way or near Andromeda or near Virgo, you get an answer that's very highly biased by that amount of matter.
right,
And so, what cosmologists have studied mainly are studying the stuff you can see. It's a lot like dark matter, which is obviously interrelated to what the subject of voids and filaments. So, dark matter, we believe each galaxy is surrounded by this vast halo, 10 times the light radius of each galaxy. So that means that if every galaxy is like that, and galaxies tend to appear in clusters, that when these galaxies are near each other, their halos overlap. And that overlapping halo, if you get enough galaxies together, produces what's called a filament. But we're biased to look at filaments. And because again, they're the things you can see. It's harder to see the voids because there's nothing in them. Well, it's not that there's nothing in them. They just have a lower than average density than the average density, and the filaments have a much, much higher density. So the reason I said it's like galaxies, we see our Milky Way galaxy, And my students here have used a radio telescope I built here to measure the rotation properties of gas clouds that have hydrogen in them. Hydrogen, the most abundant element in the universe, in our galaxy, it produces what's called a 21 centimeter emission, which is a very, very finely, almost like a laser, coherent signal, very narrow band frequency. And so that means you can use it very accurate measurements of rotation curves and Doppler shifts. So that's what we do. And we measure the Doppler shift very precisely, and we get a rotation curve of the galaxy. But that's stuff we can see. In other words, we're using the properties of luminous matter, stuff we can see, to reveal properties of matter we can't see, dark matter. The same thing happens with the voids. We can't see the voids, but we see their presence by where the filaments are. Now, inside the voids, he claims that what we interpret as the dark energy acceleration, the accelerating cosmological constant that people have talked about for the last 30 years, and Einstein
Right.
originally, he says that's a consequence of the fact that we have large scale energy gradients due to the presence of the fact that we happen to be in a void, but we're near the wall of a filament. So it's kind of cool. There's a huge gradient. We're not in the center of imagine the galaxy distribution as a sponge, and the voids are the holes of the sponge. We're kind of like right near the edge of the spongy material, but we're in the center of a very large void. And that is central to his concept, which he calls timescape, because gravitational forces make time tick slower. And regions of lower density, time goes expanding faster. And so we're basically being biased by the fact that we exist here. Now, he doesn't say that there's no dark energy. He's just saying the dark energy that we measure is an artifact partially attributable to this general relativistic effect that is not really possible to capture in Newtonian dynamical simulations. So and I should say there are other people that believe this, but he's gotten a lot of attention. I think the interview is really good. So I hope you'll enjoy it. It should be out this within a month from now before we meet again. And that void recession that he claims is not only a blow against not the Big Bang. He believes in the Big Bang. He believes in expansion. He believes even in dark energy, just not a cosmological constant. So he's getting like 10 to 20% effects in the velocities of galaxies, but he also offers an alternative that could be falsified. So he claims that actually, he will eventually have enough that we can actually get enough data by measuring more supernova data and also looking at the exact dynamics of the clocks within voids and within filaments. So he could actually see stuff if we can see, say, the 21 centimeter emission in other galaxies, or in the future redshift surveys that baryon acoustic oscillations are providing. You'll get basically clocks at different redshifts. And so you'll be able to separate out the local stuff at low redshift below Z of 1 from the high redshift stuff at Z of 1,000 that the CMB measures. So there's a couple of different tests that can be done. It's really to measure having clocks at different distances. The one that I'm most excited about are black hole mergers, because a black hole merger, when it comes together, makes gravitational waves. And those can be used not as standard rulers or standard candles, but as standard sirens, as basically known coherent sources of radiation, gravitational radiation. And if we have enough of them and we can measure enough of them with LIGO, if it doesn't get canceled, uh, or at least one of the two arms stays alive, even though that would be quite poor, still, we can measure the ticking of clocks in voids versus filaments.
Okay.
Yeah, so it's pretty exciting.
Well, looking forward to listening to that.
Yeah, no, it was a great interview. If I say so, don't say so myself. Yeah, he's in New Zealand, and he's
Oh,
kind of a
geez.
character too. So I really enjoyed talking to him. And then on Wednesday, this coming Wednesday, I have an interview with the leader of DESI. So he was here at UCSD last month, 2 months ago, and we talked about the DESI results that suggest that lambda is not accurate, and we have dark energy, but we don't have a cosmological constant, and they've ruled out.
That's totally different, though, right? The cosmological constant is a thing that they think is like 10 to the 100th off, based off of quantum field theory and stuff like that.
Well, that's a little different. So, if you tried to predict what the cosmological constant is from QFT, yes, you get a value that's 100 orders of magnitude or more than what we measure using supernova and CMB. But that doesn't mean it doesn't exist. It just means that calculating it from first principles as people have done it, you should be aware that that calculation is really a back of the envelope calculation based on these considerations called naturalness that a lot of cosmologists don't really believe is an accurate way
Right.
to
Right.
yeah.
Okay.
Yeah. So how about some more questions? I got 5 more minutes before I got to go pick up the kids. Darren, yeah, Darren, you got a question. Hold on one second. Go ahead, Darren.
Um, Yesterday I saw that Mike McAuliffe posted something about Eric Lerner. But he gave a lecture and he was saying that it was pretty good. Did you see that? Did anybody notice it?
I'm actually at the conference where that's there. Dr. Mike McCulloch is here as well.
Did you
You
hear that?
thought it was good?
Yeah, did you hear that? Did he speak yet?
Eric Lerner, he gave something. I have a couple of screenshots from Mr. Eric Lerner's presentation. We were discussing it a little bit at the beginning of the call and everything. I know Dr. McCulloch, I believe he's slated to speak tomorrow. This stuff will be up on the Demystify Side podcast probably in the next month or two. They're recording the lectures and everything. So you can judge for yourself. I mean, I'm just here to try to learn, observe, and you have to be the judge for yourself because we all have different opinions.
You're being a good learner.
Rick Lerner.
So send me some of that just in case it doesn't get or send me a link if the talks are live stream, Matt, because yeah, I can't obviously go there, but yeah, ask some of these questions if they do speak about it. Like what about the 10 to the 10th different, every single measurement of the CMB anisotropy power spectrum, for example, is consistent with the hot Big Bang, both because of the abundance of ordinary matter, of dark matter, the existence of dark energy, and we've measured just the CMB temperature and isotropy power spectrum out to 3,000 multipoles, and each one of those is a test of the Big Bang model. They all agree. And we've also measured all the different intercorrelations between a parameter, say, that judges how fast the universe is expanding, like the Hubble parameter, with the mass of neutrinos. There's no other cosmological model that both offers so many opportunities to be proven wrong and yet passes every single one of them, except for one subset. As you know, the best that they can do. I mean, I hope that I've convinced you that the surface brightness measurements, unless you always ask them for how does their theory, where are the theoretical error bars? Just tell me, what are the one standard deviation error bars? If you would ask them that, what are the one standard deviation error bars on the predictions of their model? Not forget about the Big Bang being wrong. Okay, let's say what is the evidence for your model, and if they can't give the error bars, that means they don't understand their model even to the 68% confidence level that they can make a prediction. And then you could also ask them, what's your this is the one question they can never answer. What is your explanation for redshift? They all believe that redshift exist. Some say it's tired light, which is ruled out even by the measurements between the Earth and the Moon, that there's absolutely zero change in the frequency of atomic clocks on the Moon, although they should be redshifting away due to the tired light traveling even just one light second. But all the planetary missions out to one light day in Voyager show to 14 significant figures. There's absolutely no change in the energy or frequency of radiation. So how do they explain that in tired light? If they say, well, it's not tired light, it's redshifting due to dust scattering. And then you would have to ask them, well, why do we see temperature and polarization and isotropy in the microwave background if we're just surrounded by dust? Why do we see it with the exact same acoustic horizon that we see it for baryon acoustic oscillations a million or 1,000 times later in cosmic evolution? They have no answer for any of these things, so I'm not worried about being proven wrong. Ask them to explain the Sunyaev-Zeldovich effect. Ask them to explain baryon acoustic oscillations. But the most basic thing is they can't even explain redshift. And Tolman, this is Lerner's favorite thing. Tolman himself gave up on the Tolman test, which was, this claim that the distribution of surface brightnesses is going to depend on redshift, whether or not the universe is expanding because of these two different effects. Like I said, the volume diminution and the photon redshifting, and time dilation is another one that gives you another power, which you can also account for as well. So you get this 1 over z to the fourth behavior. But in a non-static universe, this surface brightness would only increase with redshift due to the loss of energy of the photons. But there's no evidence for that. Even in our solar system, there's zero evidence, let alone at galaxy scales. So they believe in redshift, but they can't explain it. And always ask them to predict what is the one standard deviation error bar. That's all I want to see. For every single prediction, the abundance of lithium, which Lerner claims comes completely from cosmic rays. The most damning thing, though, when he mentions Tolman test, is that Tolman himself gave up on it. Tolman rejected the test that bears his name.
Got it. Error bars matter.
Absolutely. All right, gentlemen, this has been fun. Inaugural conversation. Yeah, this is super fun. Have a good weekend, everybody. Send my regards to folks there in Portugal. I wish
Happy Father's Day.
Yeah, happy Father's Day.
Absolutely.
Thanks,
Happy
guys.
Father's Day.
All right,
Absolutely.
we'll do it again soon.
Thank you, guys.
Bye,
All right,
guys.
peace out.
Bye, Michael.
Bye, Dr. Brian Keating.
Nice to meet you. Bye.
Nice to meet you too.